All right, let's get started a little bit early here. So that fourth homework is due at the end of the week. Some of the last ones you can file upload. If you really want to hand me a hard copy, you can do that. Excuse me. Early next week, I'll put up one more homework. It'll probably be a little bit more kind of regression heavy. Just kind of making sure that we're having a good understanding going into that final about thinking, if I have this question in mind, what's a dependent variable that I'd be interested in? What's an independent variable? How do I interpret some of this output, this regression output? Thinking about statistical significance, all these other things. So I'll put that up Monday after class, and then you'll kind of have the remaining 2 weeks of the semester to complete that. Okay. I'll also, probably not today, but by the end of this week, I'll get up some practice exams. I mean, we're still quite a ways out, but just to start thinking about that. And we'll talk more about that as we get closer. Right? So where did we leave off? I'm going to skip all this. I don't even know. So I've kind of got some slides up here, but we're primarily going to be going through some papers here today. And then I'll maybe do a little bit of stuff in Excel. Let's do this one first. So I've got this, I think, interesting paper, and I'm going to scroll down here until we find the regression equation. Okay. So these authors have this interesting idea of identifying something that we call peer effects. So peer effects, just in like more broad terms, is the idea of, and I'll put it, it's usually talked about in the context of education. So I'll start out with that example, and then we'll work to sports, right? But it would be the idea that if I'm in a classroom with other high ability students, that I actually will perform better, right? Because higher ability peers, maybe there's some kind of peer-to-peer learning going on. The teacher is able to talk more specifically to one group of people. And so having higher ability peers is going to improve my performance. The peer effect that we're looking at here is a little bit different, but this is the idea that not just did my peer have high ability, but did my peer have access to steroids, right? So the idea of this paper is, what happened to my playing performance when I was playing with Jose Canseco, right, compared to afterwards, right? So after kind of playing with him, or during playing with him, did I see an improvement in my performance? You know, kind of the idea of, I think they outlined earlier in the paper, like, you know, Mark McGuire maybe started using steroids as a result of being a teammate with Jose Canseco. So, and then they have just a bunch of other control variables in there as well, right? For what the player's performance was the year before, how old they were, all these other things. So that's our regression that we have in mind. We'll then scroll down. I think this one has all the tables at the end. There we go. So they kind of start out, we're just looking at averages, right? So if I looked at the average home runs for someone after playing with Seiko, currently or never, I've noticed this trend that they're increasing, right? Maybe suggesting that people who play with them are more likely to maybe use these substances as well. Now, it's not great evidence, so we keep going down. And they've got some descriptive statistics, some summary statistics. And then they have kind of all these like different players, and they're not going to hone in just on Jose Canseco, but on some of these other players as well, who are either known or highly, you know, allegedly use steroids. So they kind of have this nice subset of players. And then here we get kind of the interesting results, right? So they're controlling for things like some hitting factors, wherever their home ballpark was, what division they were in, their experience, manager's lifetime win percentage, batting average. We're trying to control for all these other things that could affect the player's performance, right? We're then going to look at these two indicators, right? So this is just an indicator or a dummy variable as a 1 if they were currently playing with Canseco, or 1 if it was after they had played on the team with Jose Canseco, 0 if not. Okay. And they then use a bunch of different performance variables, right? So usually when you see something like this, every single column represents a different regression, right? So here, my dependent variables: home runs, strikeouts, RBI, etc. Now, what they find here is that there's no real strong significance. But they do find a lot of these things are positive, right? You're more likely to get a home run. You're more likely to strike out, though, as well. More likely to have a higher number of RBIs, right? It looks, and even kind of a higher number of walks, right? So this might lend to the conspiracy theory that potentially this performance increase is in these categories where strength, right, is really going to help you hit more home runs, but also kind of being bulker, maybe it makes you more likely you're going to strike out. But we don't have a lot of significance, and they tried to include some of these like individual fixed effects. Oops. Actually, no, we might have significance. So this paper's jank, I forgot. Let's go back up here. What they did is not often done. Not really good practice, to be honest, but everyone's totally different. Instead of putting the standard deviations or the standard errors below the estimates, they're actually telling you what the t-value is. So that's why we have things like 2.3 or 2.1. So anytime we have these higher t-values, there are going to be situations where we maybe can reject, right? We maybe can reject the null. We're going to have small p-values. It's likely they're going to be less than alpha. Now, they don't really kind of indicate which of these are going to be at, what level of confidence can we reject, what level can we not. But at least we can kind of look at the magnitudes. Okay? So I'm going to go down here. What was this? I know there's a better pay table. So I want. Here, I think this is what I want. That's not a table in there. Here it is. So they did a very similar thing. But they limited kind of the regressions to more power position players. So I think this was like they got rid of second baseman, shortstop, and kind of had a smaller kind of subset of position where you usually see higher home runs. And then they ran those same regressions, found that the estimates were a little bit higher. So notice like this is 2.9, so playing with Canseco or after playing with Jose Canseco, a player's expected home runs went up by 2.9. Their expected strikeouts also went up by 8.3. This is on a season average. But then they ran this for every other player, right? All these other like expected players who were known to use steroids. And what you notice is the expected home runs, all these are negative. Looks like playing with it, this was, I don't know how very good maybe. Maybe there's a slight increase after playing with him, but like everybody else is kind of negative. So this is kind of what we usually call a falsification test. If we don't believe that any of these other players were actively distributing steroids to other players, then playing with them shouldn't have kind of this additional impact after you play with them, right? But if we have someone who is suspected of that, and not only do we not see a negative value, right? We actually see a large positive value. It's going to be a really nice indicator that playing with Jose Canseco led to, following playing with him, led to someone hitting on average more home runs. And we don't see that for any of these other kind of known or suspected kind of users, right? I don't know. Some of this is, it's not significant. So if we're looking at like Ryan Sandberg and Ivan Rodriguez, like, yeah, we do have positive values, but they're not going to be at any statistical significant level. So I don't know, kind of interesting, like first look into pure effects. But I think what's a more interesting one, and I think I've mentioned this before. If I have, let me know. So did I mention the Israeli kids study earlier in the semester where they ran against each other? I did. Someone's nodding. Yeah. So that's also the idea of pure effects, right? So just a reminder, these Israeli kids, they were making them run races against each other. And when they just they would just have them run on their own. I forget what it was, like not very far, 20 yards or something. And took their time, right? They then ran the same kids, but simultaneously, right, against another opponent. And what they found was they ran faster when running against someone else, right? And so we're going to use that same kind of idea, but we're looking at swim meets, right? So we don't have this nice kind of clean scenario where we have the recorded time of the individual just on their own, right? All we have is this swim meet data. So we're going to look at their performance, right? What their time was in this event. And I forget the exact swim events. They control for like what races. So there are all these different meter races. I'm not like a huge swim fan, so I don't know all the, what the terminology, but that's swim meets, and right, they have these different lengths. We're then going to look at the average time of everybody else in that current match or in that current, swim, right? So this is going to try to capture kind of the average quality of my peers, right? Or the average quality of the people I'm swimming against. So if we do find peer effects, if the average time here goes up of my peers, what would we expect to happen to the performance or the time of the current swimmer? This is a little bit tricky. So think about what's better to do in swimming. If you're trying to win, you actually want a lower time. Okay? So if my peers, right, we still interpret our coefficient as a 1 unit increase. So if my peers get on average 1 second slower, if there are peer effects, what we expect the sign of that coefficient beta 1 to be. So my peers are getting slower. If there are any peer effects, my performance would so if I'm running against someone who's slower, it's more likely that I'm also going to run slower. Here, if I'm swimming against people who are on average, not as fast, I don't have to swim near as hard to guarantee a win, or you can kind of tell these stories. So we might see their performance decline as well. So here we would expect this to be kind of a negative value, right? That as my peers get slower, positive value. As my peers get slower, that's an increase in time, right? So 1 additional second slower is a higher time to complete the meet. I would expect that would also increase the time it takes me to complete the meet, right? So we would expect this coefficient to be positive. We'll see if that's actually true. They also do something that's a little bit interesting here, which is, so means matter, right? I'll try to get at this idea with going back to some stat stuff you probably want to forget, but let's say I've got a distribution of performance, and we'll do the time for the swim meet, right? So there is some mean performance. Right? This is the average of my peers that I'm capturing. Right? So maybe I'm way out here. Right? So I might not put in near as much effort if the average is far below my performance ability, right? If this is where I'm at in the distribution of ability, or actually, sorry, mix myself up. Slower times are better, right? So if I'm over here, right, and I'm on, a higher ability swimmer, I can get much lower times than the average of my peers. I might not try as hard. Excuse me, but what if I had the same mean? This is a different color here. Here. So let's say that's the distribution, right? Well, it could still have the same mean. It's just that it's skewed, right? So there's these extremely large times that are pulling that average up, even though the majority of the swimmers in this race, in this distribution, are going to be of much higher ability, right? Lower swim times. So another good example, you can think of this is like, I ran high school cross country for whatever reason. I hate running, but so you'll notice in some of these meets, like there's some people who are finishing, like, I think what was a good time was like 14 or 15 minutes. There's something 40 minutes to complete this 5K, right? And so if you have these extremely slow individuals, that might pull the average time way up. But there's a bunch of people who are finishing under 20 minutes, right? It's just that your mean won't be in that kind of bulk of where most people are running. It's going to be way out here because these stragglers are kind of pulling that mean way up. So not only are they going to control for the average, they're also going to control for kind of the standard deviation, right? Or the spread of these distributions. We could even go a step further, but I don't introduce it in my 221, but you could even do things like control for kurtosis and skewness. So Let's go down here. Oh, this is going to be, where's mine? There it is. Okay. So we don't have to worry about what they're exactly doing here, but we'll just kind of look at this first column, right? This is kind of, they do some other fancy stuff, but our traditional kind of regression that I expect you to know, this is going to be their column one. Okay? So they've got what's, I think with the game type word here, it's like 50 meters, 100 meters, all these different types of events. So they controlled for using a bunch of indicator variables what type of event it was, right? So if it was a 50-meter butterfly, it was 1. If it wasn't, 0. Right? So they're controlling for the type of race that it was. They're controlling for kind of, was it like a finals match? Was it a prelims match? Like things that matter a little bit more. What was the gender of the individual, weight, height, age? And then here's kind of those variables that we were interested in, which would, hopefully tell us whether or not there's any peer effects going on, right? So what we'll notice here is if the average time of the people that the person was swimming against went up by 1 second, their performance also increased by 0.36 seconds, right? So this would be some evidence that there is some of this peer effect going on, that when my opponents are of lower quality, I might put in less effort, my performance actually is hurt as well. Right? And this is a pretty consistent result across kind of the different types of regressions. Like I said, these are things we won't talk about. We just do what we call OLS, or ordinary least squares. But pretty consistent result across these other specifications as well. Here, this is kind of an odd one to think about, but if the standard deviation of the people I'm swimming against goes up by 1 second, it actually makes my performance get better, right? And time going down is a better thing here. So why are these moving in opposite directions? So I gave you an example of like a skewed distribution, how we could have the same mean but different variances. Let's think about one like this. I really want to highlight this fact, so I'm going to draw it really extreme. So let's say here's the mean, right? And let's say my ability to perform, right? My time was somewhere out here. Like this is the individual time of individual 1 that we're looking at. Okay. Well, there's not many people in this distribution who can perform better than them, right? So if that average shifts to the right, people are getting slower, there's going to be even fewer people, right? So this person may not put in as much effort and they might see their performance decrease. Okay? That's the idea of when we're looking at the peers average time, right? That was telling us that if that mean shifts, right, if the average time increases, it's going to make this individual's performance increase as well, right? Or when I say performance increase, they're going to get slower, right? Their time is going to increase. Okay? Now, what if we have the second, so this was a positive value. What if on the standard deviation of time of my peers, we found that this was actually negative, right? So a higher standard deviation, but the same mean, right, would mean something like this. Drawing this really extreme to prove the point, right? If I have a higher standard deviation, I have a more varied distribution, right? So it gets flattened. It's more likely I see times that are really, really far below the mean, but it's also way more likely I see times really, really far, above or below the mean, right? So now if I think about this same individual, so the probability that someone in a race could beat him before, we could almost think about was like the area under the curve to the left. Now, with this new distribution that has a much higher standard deviation, yeah, even if the average went down a little bit and this distribution shifted, there's a lot more people now. That probability that someone is better than him has increased a lot, right? So this is kind of consistent with what we would think about if we're looking at these distributions. If the average time is going up. So I can even draw a third one on here. What color? This. If the average time is going up, so it's shifting this distribution to do something like this. Well, now I can't even shade in. There's like almost no probability, right? So that average shifting is going to make it more likely that that person with a high, ability to get a really, really low time or high performer, that they put any effort in at all. But even if you shift that mean and the standard deviation gets higher, you get this flatter curve. Well, now the probability there's people that could beat them is increased. There, you would actually see them maybe try harder, and that's why you see their time decrease, right? Or their performance get better. So, I haven't seen this in used in too many other sports. I always thought it'd be interesting. Like you could really do this with any race, right? Any individual sports where people are competing at the same time. You could look at what was the average quality of the peers, right? And how does that influence the performance of the individual? Okay. And if I go back here, and they find these are pretty heavily significant, right? It means 3 stars. So that's telling us that we could reject the null, that there's no relationship between the average and the standard deviation of my peers' times. We can reject the null that there's no effect, or saying differently, we found very strong evidence that there was an effect at that, even at that 99% confidence level. Any other questions on this before we keep moving? Also, I was thought this was very interesting. I would have thought height for swimmers was a good thing. But it also could be something we've talked about. Why might this not be reflecting the accurate relationship between height and these are people that are performing, or their times are going down lower, so they're taller. Actually looks like it's a good thing, right? So why might that not be actually capturing the accurate relationship between height and performance here for swim? What's another thing we could do? We said sometimes that better fits the relationship. And I won't make you interpret this like on the exam, but just to kind of start thinking about these things. We said that if I've got some variables I'm interested in the relationship of, it could be that the relationship is not linear, and I can still get an estimated, line of best fit for this. But if I allow it to be quadratic, I can get something that fits it a lot better, right? So I would, venture to guess if you included a quadratic, potentially, right? Initially, maybe height is a good thing in swimming, right? You have, more power, you have more force, you've got longer arm strokes. I got to imagine at some point that starts to decline, right? It can't be that it's just a linear relationship. You don't see a lot of 7-foot swimmers, right? There's a certain point where it becomes actually a detriment to be taller. And so anytime we're kind of confused, or we think, that seems like there could be, different kind of impact of that variable for different levels of that X variable, like the effect could be different. We might want to include something like a quadratic term, right? They didn't, but just thinking, what could they have done differently? That would be one of the things. Pretty simple paper. I think that was like their only table, right? So, pretty simple. What I then want to do is I have this betting data that I put up on Canvas. So we'll play around with this a little bit. So point out a couple things. So I have a bunch of, why won't it? What did I select? Let me see. There we go. So let's go up here, go all the way back. We've got all these different games. I've got the season. I've got what the home team score was, the away team score, what the spread was going into it, the over under. Kind of, I've got some for some of these. I've got weather information. Got the type of stadium, elevation, all these different variables. So one thing that I did starting out, and I kind of just copy pasted the data, but this could be helpful for some of you, I guess, if you're working on your projects or even outside of this class. But notice here I've got these different stadium types, right? Well, I can see some of them here, but I don't know what all the responses are. So as always, let's just start out, select our entire data set. So Control-Shift, Command-Shift on the Mac, hit the over and down arrow. I'm going to throw a filter on this data, right? Maybe, there we go. Scroll all the way up. So I've now got a filter on. I'm going to go over to that stadium variable now. And if I click on this, I can see any type of stadium that I could see. So the only responses are indoor, outdoor, retractable, and I've got some blanks in there. So I think we talked about this before, but what do I want to do with those blanks? It's missing data. Yeah, I want to delete them, right? I can't run a regression with nothing, right? There's no, that's not even a zero. There's just no value there. So I'm going to deselect everything and select just the blanks. Okay, it looks like there's just a couple observations, like for whatever reason that didn't get recorded the type of stadium. I'm just going to highlight them, delete them. Okay. I'm going to go back over. Now I can see all the different stadium types. Now I created this variable already, but I'll show you if I hadn't. We'll just delete this. I want to create, was this a game played indoors, right? And here I'll define indoors as just being retractable or being an indoor stadium. So the only observations here where this should be a 1 is if it says retractable or indoor. Okay? So I can do this one of two ways. I could use this if statement and say, okay, look, if this cell is equal to the word outdoor, well, if that's true, I want my indoor variable to be a 0, right? So what we're checking to see if it's true is the first thing that we'll use. Then if that's true, what value do I want to put in this cell? Comma, if it's not true, so the stadium type is anything other than outdoor, right? Retractable or indoor, I want to kind of label that as an indoor stadium. So comma 1. I hit enter. I then can go here where I get this black kind of plus sign, double left click, and it kind of fills this in all the way down for me. Okay. So I've got, it's kind of nice. I've got some of these other variables. And what I thought was kind of interesting, we could take a look at, is previous covered. Where is this at? No, that I haven't. Previously covered. Okay, so we're going to use the number of games that the underdog previously covered, the spread, and then we're going to look at what the actual kind of score was, right? So, or if they, if they covered the spread in the current game. So I'm looking through here, and I've got whether or not, and actually let's do the favorite instead of the underdog. So I've got basically this variable that I created was a 1 if the team covered the point spread, 0 if they didn't. Okay. I then have, did they previously cover the spread? Right. So I've got all these other variables though, and I don't really want to deal with these, right? So I have these 2 sheets. On this second sheet, I kind of created a smaller data set, right? Just for the sake of like looking at all this, right? So I've got, did did they previously cover the spread? How many games previously did they cover the spread? I've then got their win percentage, and then I have all these other variables. So how would I kind of create a data set that's smaller like this that has the variables I want? So got my raw data. I'm just going to select it all, copy it, go over here, paste the values. Okay. I'm then going to throw a filter on it. I'm going to start selecting the variables that I want to include. And I can't see this well, so I'm going to maybe sit down here so I can see the Excel open. So I'm going to make this a little bit larger so we can see what I'm doing here. Okay. So I don't really, for right now, need any of this weather data. There's a lot missing, so I'm just going to first get rid of that. Right. Same kind of thing with the elevation. I might then be interested, okay, I might be interested if it's a playoff game. That might matter. I might be interested in, is it an indoor stadium or not? I'm not going to be using kind of the total score of the game. I'm interested in eventually running the following regression. So did the current team cover the point spread? And was that influenced by the number of times they previously covered it, right? So maybe if they start covering the spread a lot, the sports book thinks they're doing something wrong, they update it, maybe it's less likely they cover the spread in the future, right? Because they're setting this line to be a little bit higher or lower depending on kind of the performance of the team. So I'm going to try to keep those variables, but also some other control variables that I want. So I don't really need to include this point differential. I don't really need the total score. I'm interested in, did the favorite cover, right? I'm not interested in the total points of the game. I've got the wins of the favorite, ties, losses. I think here I've got the win percentage. So I'm just going to delete this data. I've already created something that captures all of that, which is the win percentage. How many times did they previously cover the spread? I'm not looking at points, right? So up to this point, I've got a decent amount of stuff here. Right? So here is, did they cover the spread? That's my dependent variable. So that's my Y variable. I also have how many times did they previously cover. That's my independent variable I'm interested in. But I also wanted to include some of these other controls. Okay. So one thing I can do, I always have to have my control variables that I want to use all in congruent columns. Like they have to be right next to each other. Here, my dependent variable is kind of separating them. So you go to insert here, then just select that column of your dependent variable, move it over. You could select these, move them over so you don't have that blank column. Delete this blank column. Now I've got all these variables that I wanted to include next to each other as my independent variables, and then my dependent variable here on the left. You could have also done the same thing and had the dependent variable on the right, but just to kind of match up with how we write it, I generally try to put it on the left side. Right? So we're thinking about what we're doing. And you could delete all this other stuff that we're not using as well. So we're not going to use any of this. And then we can get like a just nice, clean kind of looking data set. Actually, I'm going to leave the years in there for now just to make a point. So I then go to data analysis, down to regression, hit OK. So my dependent variable I wanted was, did they cover the point spread of that game? So I can select that entire column of data. Now I already see I'm going to have a problem because if I try to select my independent variables, I've got some blanks, right? So that's something that's always good to check before you kind of jump into that data analysis tool, is go through each one of your independent or your X variables and say, okay, do I have any missing values? I'm going to delete this outdoor variable because we shouldn't need it. So no missing values there. Okay, there's my missing values. So select the blanks. It's quite a few. So I'm going to lose some observations here, but I can't use them if they didn't have previous data. Right? I think what those were, if I'm looking at the previous number of times they covered the spread, what games inherently am I going to lose? If I'm saying the number of times they covered the spread in a season, what games will I have absolutely no data for? Yeah, game one, right? So I lose every single first game, right? Because there's no previous games that there was a spread for, right? So I've now got this, hopefully all my missing values, kind of eliminate all of those. So I'll go over here. Did they cover the spread? Whoops. Well, go back up. There you go. That was my dependent variable. I'm then going to select all of these as my independent variables. I selected the labels. I'm going to hit OK. Get this output. I'm going to zoom in so we can actually read it. And we start to interpret some of the things that we're seeing. Okay. Now, before I even go to the coefficients or the results, why should I be a little suspect of anything here? Any of the results? Yeah, remember, our R squared is telling us how much of the variation in did they cover the spread or not, that Y or that dependent variable, am I explaining with all my control variables? Well, I'm only explaining here, sorry, it's the proportion, but we generally convert it into a percentage. I'm only explaining 6%, right? Or the proportion of variation I'm explaining is 0.06. Okay. Well, I've got 2,500 observations, though, so it's a pretty good sized data set. So I'm going to come down here and we can see, okay, here's the variable that I was really interested in, the number of times they previously covered the spread. And what I find here is it really doesn't influence whether they cover the current spread at all, right? I mean, I guess we would interpret that if they've covered one more game previously, maybe the probability that they cover this time goes down by 0.002. Now, remember, anytime we have a dependent variable that is a 1-0, the interpretation here is a 1 unit increase in X. So if they covered one additional game, so I guess here covered one additional game, the probability of the Y variable, right, going from 0 to 1. So the probability of going from 0 to 1 is that they cover the current spread changes by whatever that coefficient was, or in our case, decreased by about 0.002. So, changes in probability are always going to be small, right? I mean, what's the largest change you could ever see in a probability? It could go from 0 to 1, right? So 0.002, although it's small, I mean, even changes in the probability of 0.1 or 0.2, that's a 1 or 2% increase. That's not, depending on what we're looking at, it's not necessarily that small. So we found that there was a pretty small effect, but we also, with a p-value of 0.58, can't really say much, right? Because we only reject the null, and the null is always that coefficient is 0. There's no relationship between this X and Y variable. Well, in order to reject that, we need the probability of the estimate we found to be less than these threshold alphas we set, which kind of correspond to 90, 95, and 99% confidence. Here, my p-value of 0.58, it's not going to be less than any of those, right? Not even close, right? So, we go back here. Okay, so we had some inkling that there might be a relationship there. We didn't find one, but what might be more interesting is look through and see, well, what kind of, what has a small p-value? What looks like it's significant here? So 0.03 is pretty small, all right? So this might be suggestive of, okay, this has a significant effect. If it's a playoff game, right, just a 1-0, so going from the 0 to the 1, then the expected change in the probability of covering the spread actually goes down, right? So this is telling us that for whatever reason, these point spreads being set are less likely to be accurate, right? The team's less likely to cover that. This isn't 0, right? It should be a 50-50 bet. So if it's truly the 50-50 odds, we should have like nothing has an impact. Here we find something that does have a significant impact. So this would be the idea that for these playoff games, the odds aren't being set correctly, right? And maybe that's being a result of what we talked about last class. So all these lines I used were the day of the game. So what might be occurring for playoff games? The line starts out as a 50-50 bet. We said, what are the companies trying to do? All right, so we're trying to get this expected value to be 0. So we had the amount of money, right, that came in on one side times the probability that this team covers plus the money that came in on the other side times the probability that they don't cover, right? Well, if we're seeing that these playoff games matter, we would have to believe that these lines are adjusting because more of the money is coming in on one side. So initially they set these as 50-50 bets, but as more of the money comes in, so let's say more of the money comes in on that the team doesn't cover, right? Well, now this is not going to be an expected value of 0. I want these two things to be equal, right? So when one of these things occurs, one's positive, one's negative, right? I pay out, or either have to pay out the people that cover, pay out the people that don't. Okay. So if the amount of money on one side starts to get lopsided, what I need to do is decrease the probability that I see that occur. How can I do that? Well, I make the line, I make the spread larger, right? So maybe in playoff games, the amount of money coming on one side, could be influenced more in a playoff game than during the regular season. So that's maybe why we find a significant effect there. Look at some of those other things. So 0.3, about 0.3, whether or not it's an indoor stadium doesn't really seem to impact whether or not they cover the spread. Looks like the sports books are accurately kind of factoring that in to what their odds they're setting are. The home team being favored. Once again, this is something that they kind of set they're kind of baking into their lines as well. But then the win percentage of the team that's favored and whether or not they cover the spread actually have like a positive effect here. And it is highly significant, right? So anytime we see these ETH and negatives, that means move the decimal that many places to the left. So this is essentially a p-value of 0. I can reject at any level I want here. So, this would be suggestive of if a team's win percentage goes up, right, that they're actually more likely to cover that point spread. Right? So this might be something like, the sports books aren't accurately capturing the quality of the teams, right? Maybe they think they are, but this would suggest they're not. Now, this is a naive regression. Remember, I said any of these interpretations, we've left out a lot of other things that matter here. If we wanted to, we could probably start controlling for things like offensive, defensive ranking of the team and the opposing team. We could do, a bunch of other controls here, because the real power of regression, right, is what we're really saying here. Like, for instance, the playoff game one. If this is if the game being played, take 2 games. They're both being played indoors. The home team is favored in both of them. They've previously covered the same number of point spreads. They have the same winning percentage, but one of them is a playoff game, the other's not. The additional change in the probability that the team covers a spread is going down. Okay? So, that's a lot more powerful of a statement when we can say holding all these other factors constant. Okay? And that's what you want to do when you're making your interpretations for your projects or any type of regression. Not only, and I get a little bit lazy with it when we go through these papers, but for instance, not only here were we saying that the average time of my peers goes up by a second, my performance actually goes up by 0.36 seconds, holding everything else constant. So this would be 2 individuals, two individuals. They're both racing in the preliminary match or not, both racing in the finals match, not, depending on the same gender, same weight, same height, same age. They're in the same race, it's the same year, but one of them, or even controlling for the standard deviation of the peers, but one of them is racing against peers that are a little bit slower, right? 1 second slower. What's the change in their performance? So that's a lot more powerful of a statement when you can say holding all these other things constant. Questions on this? I feel like I'm just talking a lot today. So, I'm not gonna let you out of here quite yet, but close. Just like to get an idea, and I'm gonna write some of these things down. So we've got 2 weeks. I've got one topic that I think there's some interesting papers on. And we'll start reworking some older models so we get a little bit more practice. We'll kind of revisit some of those homework 3 questions, and then once homework 4's due date is passed, after this week, I'll kind of revisit some of those. But is there any topic that anybody, or it's a question that's happening that's relevant, that's happening now that anyone's interested in? Nobody's interested in any sports or anything that's happening going on. Yeah.
I'd say, like, I guess the MVP race right now, there's like a lot of argument with Joel Embiid, even though and PER wise, he's not even close to.
Right, so I might pull in some advanced statistics. Okay. Do you have something?
Yeah, I was thinking, like, at least in baseball, the impact of rule changes, so the whole expansion of bases, or even just how they've eliminated division play by 60 games in the future league play.
Think about some of those things, and I can also look for current papers on these things too. Anybody else? It's have to be like a main sport to be anything. The teams do something they do. I have an idea of something. I have one that I'm thinking about because it's somewhat relevant, but like draft trade decisions.
Like the effect of like the play-in tournament, and the NBA on like
Yeah.
targeted number of wins for.
Yeah.
For teams.
Anything else?
Specifically with like the playing tournament, like the debate on if the Clippers should have thrown the last game, dodged the Suns.
Yeah, we talked a little bit. Oh, I see. We talked about something different before class. On matchups. Okay. Anything else? All right, that gives me a decent kind of list to start working on some stuff. I don't know if we'll go through every single one of these, but I'll try to touch on them and maybe find some papers or kind of use some of our old models to understand them, maybe introducing a new model here or there. I'll also bring in a little bit of my own research. I've got a lot of stuff I've been doing on like basically basketball shooting data. So I'll bring in some of that because it's got some interesting results. But I will definitely, some of these would be some really good things we could talk about. They'll hit on some previous topics and things that you expected to know in the final. So other than that, any questions from me before I let you guys get out of here today? Also, I know it's gorgeous out, so I appreciate all of you taking the time out of the day to show up. So I will see you guys on Friday. I've often